It's my great pleasure to summarize the physics and simulation session. We have 4 conveners, Patricia, Yaquan, Jenny, and me. First, I'll give an introduction for this kind of E collider. E collider exists as a precision machine because we have 2 ways to search the new physics. One is directly. Search for new particles or new phenomena, something like Higgs and multi-quark states. And the indirect way is the E collider. The main approach at E collider is precision measure some fixed parameters and compare with the theoretical prediction. If there's some difference, this means something new physics. So the examples is measure the Higgs double boson, Z boson properties precisely and compare with the fixed prediction. And to realize this kind of goals, some precision goals, we need a lot of preparations, something like detector software and new technology of software tools. And we need a collaboration with the theorist and final study and some kind of high order corrections and the analysis. This some kind of iteration. In our parallel session, there are 4 sessions and 16 talks. There was a lot of fruitful discussion. We have 3 talks from the final and theoretical, and 3 talks about detector software, and 10 talks about the analysis. First one is the CPC baseline detector design. In the pre-CDR, we have the CPC1 geometry. After many works, we optimize the main parameters of our detector geometry, something like the track radius and the magnetic field, and even we investigate the time of flight technology and the DDX for PID, and the calorimeter cell size and the number of layers, something like that. We convert to a new version of CPCV4. So this data has been optimized and validated. Our software tools get more material for the data optimization and analysis. And we also prepared a lot of tutorials and documentation for the newcomer. This is our screenshot of our software website. This is analysis software chain, and this is the key elements of our software, something like generators and the data formats and the simulation software, digitization, and all the reconstruction top on the high-level reconstruction software, and also general analysis framework. Even for the fast simulation, we provide some tools for the theorists to do some fast look for the simulation. We also have an alternative detector option, ideal option from our Italian colleagues. This data concept has can satisfy our fixed requirements. It also has some extra advantages, something like for the main drift chamber, it's very strong and large, and it has the ability for the cluster timing for the reconstruction and also for the PID DDX. So we also have a talk on the new technologies, the so-called machine learning, deep learning, because it's very promising technology for the future high energy physics, environment physics. It can be also used, can be used for almost everywhere, something like DQ, trigger, reconstruction, and PID tagging, fluid tagging, and also analysis. Even for the simulation, they can use some tools to simulation our pattern shower in the calorimeter very fast, also for the final study. And it's very efficient, fast in application stage, and it's also very efficient. We need less or even no coding work, so it's a big advantage. And it has potential performance gain for actual improvement because in principle, more information can be used in the deep learning framework. And it also benefits from industry development because There's a lot of application in the industry area, something like Google and the big companies. But there's still a lot of work should be done for our HAP area. But the future, I think, is very promising. This the big part is mainly focused on the analysis and the physics. First is the global picture. We have a talk from Kylie for the Higgs combination. This is the current status of all the Higgs properties after combination. We use different frameworks, 10-parameter and 7-parameter framework to fit all the Higgs analysis results. Update the fit iterationally from the pre-CDR to now current states. And the correlation are taken into account in the simultaneous framework. And these results will be used in our future CDR and white paper, Phys white paper. And for the Higgs to default to final states, there's a long time work for this kind of analysis. The pre-CDR results is based on the CPV1. Now we try to update this results in the new data geometry. We call that the 3 Tesla framework. The results are consistent. And for Higgs to mu, this suffers more from the lower magnetic field because the tracking momentum resolution is more sensitive to the magnetic field, B field. We can see that this result, the combined result is for CPV1 is 16%. And for the 3 Tesla and 3.5 Tesla, the precision is a bit worse. For Higgs to tau, this analysis, for this analysis, we develop a dedicated tau founder algorithm for this analysis. And this analysis also benefits a lot from the precise impact parameter measurement. Also, the PFA-oriented detector is very essential for the tau founder use. This is for two tau lepton and 2 jet events. The philosophy of tau founder is something like this. We use cone angle to select the tau candidates. This is a so-called pole distribution, and the signal is here, and the background from the Higgs to WWW lab full leptonic or semi-leptonic decay backgrounds. This is a combined results we can get sub% precision. For Higgs to WW, this channel is very important, not only for itself, it's also for the Higgs width measurement. It's a very important input for the Higgs width, but this channel is very complicated because there's a lot of number of combination in the W case. All these results is from the CP31 geometry, but we start to update the analysis from this final state. This is the W fusion. This is also very important for Higgs width because it's one of the input. In the CP1 analysis, we just fit to the record mass distribution to extract the signal. Now we try to 2D fit, but it doesn't improve much. But we use the new trick to improve the mass resolution. That has improved significant improvement. For the Higgs to envelope decay, this result I think is based on CP1 geometry. We get 0.24 upper limit for the Higgs envelope decay, and it's much better than the Atlas SMS because their upper limit more than 20%. This is 3 different channels and the combined results. For the Higgs to digest analysis includes the BB bar, CC bar, and the gluon-gluon pair. And this channel is very important because it's a very good test bed for the Philip-Tagan check. Now we use a three-dimensional template fit, and the systematic evaluated carefully because this work was referred by very senior people. And we also use a new tailored machine learning approach because the main background from Higgs decay to WW and Z pair, their hadronic final state is very difficult to be separate from our signal, especially for the BB and the gluon-gluon. So we use the CN to determine the number of jets. So the W and the Z pair final states has 4 jets, but our signal is only 2 jets. This is a 3D projection of 3D fit results. This is the combined precision for the BB, CC, and gluon-gluon. This is the electroweak study besides the Higgs. The summary is by Zhijun. There's a lot of topics, and the current precision is at CPC. And we also have 2 talks on the W mass measurement. Hena gave an overview talk for the status of direct method and the threshold scan method to measure W mass. We also discuss possible techniques such as kinetic fit, and the main challenge is for the direct method is the systematic, something like the jet energy calibration and the color recollections and both Einstein correlation, something like that. This is the plot from CPC simulation, and this is L3 results. For the threshold scan method to measure W mass, it's very interesting and very promising, can reach very high precision. In our assumption, we take data, baseline data taken plan is 3.2 inverse alpha. And we have this kind of assumptions on the efficiency and purity and correlated to the systematic error and the beam energy calibration and beam energy spread and the beam energy uncertainty on the beam energy spread. This is a different data taken strategy. We can reach the different kind of precision. More or less for the W mass, the precision about 1 MeV, and for the width of W is about 3 MeV. Two very interesting points is here. At some points, some kind of systematic error is not very sensitive to our result. So in our strategy, we tend to do the data taken at this kind of points. There also a talk about the differential distribution analysis to extract the standard model and anonymous couplings. They used at most 5 variables and the full analytic calculation of the angular distribution to extract the couplings. It can get very, very great precision. This is not all the data set, only one channel. That means it can be improved further. And there's also some finite study about the 2 Higgs doublet plus a singular at the E collider. We can see that at this kind of model produce very nice work results at LHC. It also has some impact on the E collider. This kind of actual scalar can affect our cross-section for ZH and the W fusion in a significant way. If we make the precision measurements on this kind of cross-section, it means we can get some signal from new physics. And another important factor in our precision analysis is the ISR correction. It's extremely important at the E collider. The talk also covers the muon collider. The ISR is important for S-channel Higgs production is directly E annihilated into Higgs boson. But in our case, it's a threshold production for the ZH cross-section measurement. We claim we can, both for CEPC and FCC, we claim we can reach the precision sub-percent, something like 0.5% or even better. But this kind of correction can change the cross-section almost 20%. So the accuracy calculation of theoretical calculation is very important. And another point in the for a realistic measurement of cross-section, in this formula, we can see that we need the input, the cross-section line shape below the threshold at the input in this kind of convolution as the input. So that means if we take the theoretical calculation as the input, that means some kind of model dependent. So this point, this line shape should be from environment. But this from environment means a lot of data taken time. That means money. So the strategy here is also very important. So that's my summary. And for the CPC detector optimization, it goes very well. And we have material software, and it has been validated and checked and used for benchmark analysis. Our analysis covers Higgs, W, and Z physics. We also tried the differential distribution study, tried to produce interesting results, and a high order correction being considered and in the final study. It's very important. New technology is making high energy environment different, so we will try to use this method and employ its ability in our work. And the precision of E collider will need the collaboration from three sides for the software tools and the analysis and the final study theoretical to guarantee the precision. So I think all the energy E collider, high energy E collider projects can share some common efforts. That's also important for our projects and fit goals. Thank you.
Okay, thank you. Any comments?
I wonder if there was some discussion about standardizing software tools for this kind of analysis work, and also I noticed that sometimes the predictions of CPC and FCC are much more different than what you would expect just from scaling for the different luminosities. So I don't know. I mean that it seems to me that better communication could help in trying to resolve these differences.
So we need more communication and collaboration. Yeah.
What about the software?
Our software can set. I think FCC also uses ILC soft based from ILC. We also use that, and our software we add some new functions for the reconstruction and analysis, even for tracking. And FCC also develops their own packages. But anyway, we can share something.
Okay, thanks.
We need communication.
Thanks for the very nice summaries. As I see it, there's basically two roles for this work. One is to build the physics case for the collider that's being proposed, which I think is very clearly done in what you've been showing today. But the other is optimizing the detector and pushing the design choices. And I wondered if you could comment on what plans are to use these sort of studies to understand the correct detector to build.
Could you repeat your question?
Are there plans to use studies like this to inform choices about what detector technologies to use?
In our detector optimization, we tried different options. We also have the full silicon. We also try to use the time of flight for PID for flavor physics. And I think we try to merge the optimize the detector can work both for flavor and Higgs, hydrogen, Higgs. This work are going. This kind of work are going. So it's very challenging. It means different detectors.
Okay, so let's thank speaker again.